Hello, my name's John Gilkison, and I'm shooting this video to go with a blog I'm writing at EV World with the title 100 miles per gallon and 100 miles per hour. And this video is showing a graph and the mathematical calculations that lead us to the conclusion that a Chevy Bolt electric vehicle with a body form with a low drag coefficient of 0.12 would be capable of 100 miles per gallon equivalent at 100 miles per hour. And one of the bases for this is this graph that I'm showing on the computer monitor here, which shows road load for an idealized vehicle, and it breaks it into the aerodynamic drag, which is in the yellow right here, and the rolling resistance, which is in the blue. So I'm going to have to zoom in so you can see this. So here you see the rolling resistance, and down at the bottom we have the speed in kilometers per hour. So at 100 kilometers per hour, it's 62 miles per hour is one of the calculations we did in our blog. And that's this line right here. And I did the additional calculation of 161 kilometers per hour, which is 100 miles per hour. And that would be just to the right of this 160 kilometer per hour line right here. And I'm going to have to scroll up here a little bit. Well, basically, you see I came up with, it's 8.25 kilowatts for rolling resistance for this vehicle at 100 miles per hour. And you will note here that the engineer, the Japanese engineer that set up this graph, has expressed this internal combustion engine car in power requirements in kilowatts, not horsepower, which we typically use in the United States. Now, right up here at 42 kilowatts is the total aerodynamic loading for this idealized vehicle at 100 miles per hour. Let me scroll back here now. And this whole graph is devoted to, although the engineer did not say, he was talking about mid-sized cars like the Honda Accord, and the engineer works for Honda. So we took the 1996 Honda Accord four-door sedan, which has a coefficient of drag of 0.32, frontal area 21.32 feet, and a CDA of 6.73 square feet. Total weight 3,000 pounds, and it's about 32 miles per gallon on the highway. So that's this graph. Now the multiplier is right down here. To convert kilowatts into horsepower, you have to multiply times 1.3409. And there's a bunch of stuff on here about accessory losses and so forth. But anyway, I want to go ahead and get out of this now and go over to Microsoft Office Publisher. And the reason I'm using Publisher is so I can zoom in. And this is power in form terms. And basically, 1 kilowatt hour is set to 3,412 BTUs. We're saying a gallon of gas, 87 octane, 10% ethanol in the United States, runs 111,836 BTUs. So hence, there's 32.777 kilowatt hours in a gallon of gas equivalent. And if you converted, figuring 88% because of charging losses, you'd actually require 37.25 kilowatt hours to charge batteries to this gallon of gas equivalent. But I only consider that when I'm doing cost analysis. A gallon of gas weighs 6.138 pounds, and I describe what a drag coefficient is. It's an idealized number, usually less than 1. It represents a reduction in aerodynamic drag over an idealized frontal area. It allows the air to assume laminar flow and come back together behind the vehicle with reduced disturbance. Modern cars typically have a CD of 0.32. And then I give an example of how a CDA is calculated. Weights are given in avoirdupois. And I've given here the kilowatt conversion to horsepower, and multiplier is 1.3409. Rolling resistance is related to weight, and it's a linear function. And aerodynamics is related to drag, and it's a cubic function. It has to do with the speed. It goes up with the cube of the velocity. That's that one. I'm just going to exit here, come back in, and do this next one here. Okay. Doing good here. This is a Chevy Bolt at 62 miles per hour with a CD of 0.12. There's your frontal area, your weight and everything. EPA rating with people in it's 3,950 pounds. Transmission efficiency, it's only got one gear, 98%. So the road load at 62 miles per hour is calculated to be 9.357 horsepower. The aerodynamic load is calculated to be 4.941. So you can see here in this example, because of the low drag form, that the amount of horsepower that needed to overcome rolling resistance is about half of what the road load is. But in a normal aerodynamic form of cars today, they would be about equal. So you have to add these two together. You come up with 14.289 horsepower. You have to convert that to brake horsepower, and that's just 0.98 transmission loss. You end up with 14.59 brake horsepower, and then you have to convert that to pounds of fuel. So you multiply that figure times the brake specific fuel consumption. I have these two numbers backwards. I'm going to have to reverse those two letters there. And the brake specific fuel consumption for this vehicle is 0.1397. That allows you to end up with 2.038 pounds of fuel. There's 6.138 pounds in a gallon. So you end up with 0.322 gallons. And then you multiply that times the, you divide that by the 62 miles per hour, and you come up with 187.6 miles per gallon. So that's pretty straightforward. So the standard Chevy Bolt with a 0.31 drag coefficient is rated at 110 miles per gallon on the highway. So lowering the drag coefficient to 0.12, it would go up to 187.6 at 62 miles per hour. So that's the first set of calculations. And now we're interested in, here we are, skip some of the preliminaries on this one. We're interested in what this car would do theoretically at 100 miles per hour. Now I realize that you can't drive on the interstates at 100 miles per hour, but we wrote a whole paper on that, that if you could, and the interstates were modified slightly to with a third lane and set up to do it, with special licenses and you had this low drag form, you could still get incredibly good fuel mileage. So the road load at 100 miles per hour turns out to be, and that's the rolling resistance, turns out to be 14.565 horsepower. Now we had to move to S-rated tires because the low rolling resistance tires on the Chevy Bolt aren't rated to do 100 miles per hour. So there's a 4% loss at least in fuel efficiency because of using S-rated tires, but we'll get to that later. The aerodynamic load turned out to be 25.243 horsepower. And when you add these two together, you come up with 39.909 horsepower, and multiplying 0.9 times 0.98, that converts it to 40.806 brake horsepower. And when you convert that into pounds of fuel, it turns out to be 5.705 pounds. And times the pounds in a gallon, you end up 0.9287 gallons of fuel. And divided that into 100 miles per hour, you end up with 107.67 miles per gallon. And if you used a 0.6 multiplier, 9.6 multiplier, to take into account the S-rated tires, you'd end up with 103 miles per gallon equivalent. And we believe with the variables, with this low drag aerodynamic platform, that a Chevy Bolt with a 0.12 drag coefficient would be routinely capable of getting 100 miles per gallon equivalent at 100 miles per hour. And that's our math to show it. It's based on that graph on an idealized body of a 1996 Honda Accord. So I hope this helps with the blog. I'm posting a link for this blog on the at the blog for this video at YouTube. So this video is meant to be viewed in conjunction with that blog. And many thanks to Phil Knox of Sanger, Texas, who helped me with all these compilations, and his name is on the blog as a co-author. So thanks a lot. I hope this helps clarify some of the mysterious mathematics. See you later. Bye.